Good afternoon, students. Today we are going to study the second lesson. To understand the second lesson, you must have listened or attended lesson 1. In the previous lesson, lesson 1, we looked at a chemical bond, and we said a chemical bond is the force of attraction that binds the atoms, molecules, or ions in different chemical species. We looked at the causes of a chemical bond. Why do atoms combine to form a chemical bond? There were two concepts. The first concept is the concept of lowering energy. When the two atoms combine to form a bond, there is an overall decrease in the potential energy of the combining atoms. As you are all aware, when the energy is low, the compound is stable. The second concept is the concept of the octet rule. When the atoms combine, the electrons in their outermost shell arrange themselves in such a way that they attain the noble gas configuration, hence becoming stable. We say the chemical bond may be ionic, covalent, metallic, as the case may be. We also defined what an ionic bond was. An ionic bond is the bond formed by complete transfer of one or more electrons. An element which has transferred electron acquires a positive charge and is called a cation. And that one which has gained the electrons acquire a negative charge and is referred to as an ion. We looked at the properties of an ionic compound. We said they have high melting point and boiling point. The reason being they have strong electrostatic force of attraction. They conduct electricity in molten state and also in aqueous state. Why? But not in a solid state, because they have strong forces of attraction. They are soluble in polar solvents with the principle of like dissolve like, and so many others. We looked at covalent bonds, and the covalent bonds, we said these are bonds formed by sharing of electrons between two atoms of different electronegativity or similar electronegativity. If the sharing is between two atoms of similar electronegativity, that type of bond is called nonpolar covalent compound. And if it is between two different electronegativity, that compound formed is called polar covalent compound. We looked at the pi and sigma bonds and so many others. Today, we are going to look at the concept of hybridization. To understand the concept of hybridization, let us look at the configuration of carbon, or look at an example of carbon. The electron configuration of carbon is 1s2, 2s2, and 2p2. If we feed the electrons into their respective orbitals, we have 2 electrons in the 2s orbital and one electron in the 2 different p orbitals. There is an empty orbital. So when we look at the configuration of this carbon, it means that carbon is a bivalent element. But in actual sense, carbon is a tetravalent element. Why? Electron in the 2s orbital is promoted. Electron in the 2s, one of the electron in the 2s orbital is promoted to the empty p orbital, resulting into 4 unshared orbitals. This gives rise to the 4 half-filled orbitals, which accounts for the bonding capacity of the 4 bonds in the carbon. This type of state is known as excitation. In most of the carbon compound, all the 4 bonds of the carbon atoms are equivalent. The equivalent character of the bonds can be explained with the concept known as hybridization. So hybridization is the process of mixing up of different atomic orbitals of the same atom, having approximately equal energy to form new equivalent orbitals known as hybrid orbital. The new equivalent orbitals are generally similar in all respects, in size, energy, shape, and orientation in space. Therefore, the total number of hybrid orbitals produced is equal to the total number of atomic orbital mixed. Let us look at the type of hybridization. We have the sp hybridization. This is the mixing up of one s and one p orbital to form 2 equivalent sp hybrid orbitals situated at an angle of 180. When we look at the characteristics, each sp hybrid orbital has 50% s and 50% p characters, resulting into a linear hybridization. An example is beryllium fluoride. When we look at the orbitals, this is the s orbital and the p orbital. Under hybridization, we get this. And each orbital is having 1 electron, whereby the orbital in fluorine overlaps with the 1 electron on beryllium, and similarly on the other side to form a linear molecule at an angle of 180. sp2 hybridization. This is the mixing up of 1s, 2p orbitals to form 3 equivalent hybrid orbitals directed towards the corners of an equilateral triangle at an angle of 120. An example is boron fluoride, and the characteristic of such hybridization, all sp2 hybridized orbitals are equivalent and have 1/3 s character and 2/3 p character. The 3 sp2 hybrid orbitals lie in one plane, and any 2 sp2 hybrid orbitals are at an angle of 120 degrees. When we look at the orbitals, this is the arrangement. We have the s, then p, x, py, which hybridize to give a trigonal planar at an angle of 180. And each of these orbital is having 1 electron, which is bonded with the fluorine to get 120 degrees of the form the triangular planar structure. sp3 hybridization is the process of mixing up of 1s and 3p orbitals to form 4 equivalent sp3 hybrid orbitals directed towards the 4 corners of an irregular tetrahedron at an angle of 190 degrees. An example is methane. And the characteristic, each sp3 hybrid orbital possesses 1/4 s character and 3/4 p characters. The 4 sp3 hybrid orbitals are directed towards the corner of an irregular tetrahedron, resulting into a tetrahedral shape. When we look at the orbitals, these are the arrangement of the orbitals, and each orbital is having 1 electron, which is bonded with 1 s orbital of hydrogen, another one s orbital of hydrogen to form a tetrahedral structure with an angle of 109 degrees. sp3d hybridization, the process of mixing up of one s, 3p, and one d orbital to form 5 sp3d hybrid orbitals known as sp3d hybridization. The point to note here for sp3d, all the 5 sp3d hybrid orbitals are not equivalent. 3 sp3d hybrid orbitals are at an angle of 120 equilateral hybrid orbitals, and the remaining 2 are at an angle of 90, which is axial hybrid orbital. Let us look at an example of phosphorus pentachloride, and we look at its orbital. This is the arrangement of the orbital, and the chlorides with the dotted lines are the axial chloride, which are at 90 degrees. Then these ones, which are very visible, are the ones which are known equatorial chloride, equatorial chloride, which are at an angle of 120, resulting into the structure known as the trigonal bipyramidal. sp3d2 hybridization. This is the process of mixing up of 1s, 3p, and 2d orbitals to form 6 equivalent sp3d2 hybrid orbitals directed towards the corner of an irregular octahedron known as sp3d2 hybridization. For this type of hybridization, all the orbitals are equivalent and they are directed towards the corner of an irregular octahedron. An example is the sulfur hexafluoride. The orbitals are as follows. They are all equivalent, resulting into an octahedral structure at an angle of 90 degrees. And lastly, let us look at sp3d3 hybridization. This is the mixing up of 1s, 3p, and 3d orbitals to give or to form 7 equivalent sp3d3 hybrid orbitals known as sp3d3 hybridization. A point to note for this type of hybridization, all the hybrid orbitals are not equivalent. 5 of them are at an angle of 72 degrees, while the remaining 2 are at an angle of 90 degrees, giving rise to the formation of a pentagonal bipyramidal shape. Let us look at the orbitals. So this is the arrangement of the orbital. This is the pentagon, giving rise to 72 degrees and also 90 degrees, resulting into the structure known as pentagonal bipyramidal. There is a pentagon in the structure. An assignment I can leave you with: predict the shape and the structure, shape or structure, the number of lone pair or pairs, and the type of hybridization of the following molecules: the fluorine tetrafluoride, chlorine trifluoride, hexagonal difluoride, sulfur tetrafluoride, hydrogen fluoride, and sulfur dioxide. Maybe it remind you a bit, how do we predict the shape or determine the number of lone pairs? In the first year, you studied this, and they said to predict the shape, you must know the group of the central atom, add on the valence, the total you get subtract of the bonded electrons. Then the answer divide by 2. Let us look at an example of water. The central atom is oxygen. Oxygen is in group 6. The valence of oxygen is 2. Bonded electrons, there are 2 electrons from hydrogen 2 electrons from oxygen. So the total number of electrons is equal to 4 electrons. If we add the group, which is 6, plus the valence, the total is 8. Then subtract of 4, we are going to get the answer 4. Divide by 2, we are going to get 2. And this means that oxygen is having 2 lone pairs. So with that assistance, you'll be able to answer the assignment given to you to predict the shape, the number of lone pair, and the type of hybridization. Next time, we are going to look at the theories. We are going to begin with the valence shell electron pair repulsion theory, call it VESPER,